Hello, check. Hello, check, check.
Okay. Okay. Hello, everyone. So, welcome to everyone for the first colloquium semester. So, I'm happily announcing that we have Professor Ramaswamy from IISc, who has been honorary professor and has been the national science chair now. So, it will be a long that I have to read through because I think it will be may skip it, but I think it's worth reading through just to let you know he is. So a little bit, he got his PhD from Chicago and did his postdoc before joining ISC as a faculty in University of Pennsylvania, and he has been also director of TIFR Hyderabad as a founding director. So he has a long list of. Fair enough. Okay. So, and he has a like accolade of awards that he received. Bhanti Bhatnagar Award in 2000, Infosys Award in 2011, and he has been jury for the Infosys Prize from 2014, and he got recognition from the Royal Society in 2016, Firoda Award in the same year. Award in the same year, and he has been elected as the international member of US National Academy of Sciences last year 2025. So this is all lists, but like I think he is more known for creating a field which he is going to talk about a little bit in a slightly different heading, matter, what is called active matter. So he is one of the fathers of the field who actually started the. Okay, so the entire field was created. One of, and if you don't know, is another the whole surge of biophysics and approach to. Okay, so Indians around the country who approached and proceeded in statistical biophysics. One of the reasons for that. So all awards cannot capture the content. But with all that, let me just invite him so that we can to say and teach us.
Um, First of all, thanks very much, Ankur, for that overly kind intro. Uh, and it's I really like addressing student audiences, so my talk is aimed mainly at you guys. And I think we can make a rule that if there's questions at the end, we should make the students ask questions first. You guys give them time. But thank you very much for this. Delighted to be here. Two of my former PhD students are in the audience, Tapan and Ranjan. It's great. It's always good to talk in front of people who worked with you. Of course, one of the troubles with talking in front of old friends is they'll probably recognize some of the slides. I'm not sure if absolutely every slide on here is new. Luckily, since they're not on celluloid, they don't show signs of age in the same way. Okay, let's see what the range of this device is. Okay, so in part out of sheer in part out of desperation not to call the talk the same thing over and over again, I've this title, and I'll tell you work on. A fair fraction of the talk work of Roshan and Shubhendra and Pankaj, and these two are at this point recent alumni from the group, and these guys are my group. So I'll introduce the subject. I'll sort of lay a foundation, and then tell you it'll be kind of one of those excessively fast guided tours through several things. I'll try not to make it very overly detailed to give you an idea of the range and the sort of the fun of the subject, and I'll try to speculate at the end about what you might want to think about beyond this. Okay, actually, these glasses don't work. By the way, is the audience fully physics or other subjects also? How many of you are not from physics? Okay, this is a small number. All right. Many of you, I mean, all of you must have done statistical mechanics and thermodynamics. And the way they teach systems is it's about systems at thermal equilibrium. And told is that if you have an isolated system, it is uniform on the set of all allowed microstates subject to a constraint of constant. And if it's a subsystem of a larger system, then this total energy is constant, and the subsystem then sits at temperature. Its energy fluctuates a little bit. In either of these cases, you know the rules. You basically maximize entropy subject to the available constraints, and that condition alone tells you how to work out the phase diagram. And it tells you not only it tells you not configuration probabilities, it tells you what the thermodynamic state will be at a given value of, for example. And that thermodynamic state essentially is the entropy maximum subject to whatever constraints you imposed. In particular, when a system when a collection of particles spontaneously arranges itself into what looks like a structure, that regular structure is achieved by maximizing, right? So if you took, for example, a bunch of rods with no other constraints, they cannot overlap in space, then at low densities, the maximum entropy state is with these rods all pointing randomly. The same system, if you just increase it and do nothing else, its maximum entropy is a state with order, right? It's just worth keeping in mind. And then you can do everything. You can look at the statistics of, you can look at dynamics by different this entropy as a function of configuration, which gives rise to thermodynamic, predict what the system does in time, and so forth. This is all for system equilibrium. And an important property of systems of thermal equilibrium is that that stationary thermal equilibrium is invariant under time reversal. If you took a movie of a system that has settled down to thermal equilibrium. It will explore various configurations. Things will change in not very interesting ways. And if you play that movie backward or forward, it will look the same. So basically, you can't, so that's not much of a movie. Nobody will come to watch it, actually. So you can't write a novel about a system at thermal equilibrium. But what is open-driven systems? Life happens in open-driven systems. These are systems not at a fixed energy budget, but a fixed energy throughput. So you get entropy source, you do something with it, and you throw out waste. When systems of this sort order, life emerges in some place, that takes place by entropy maximization, but by local entropy decrease. So it's curious. Both cases, I talked about order. One case, a collection of particles lining up, or a collection of particles arranged in the crystal, maximizing entropy. The kinds of structures we are interested in are structures which are created by local entropy production. You decrease the entropy load, you throw out a lot of heat, and you create ordered, structured states. We don't understand the general law in these systems. What we do know for sure, even when systems of this sort settle down into a time state, it's a state that's not time reversal invariant. If you take a movie of what's going on in one of these systems, even if it's a very long movie of a system in stationary state, that movie played forward and played backward will look different. Okay, it's worth keeping that in mind. So in particular, what that means is if you're trying to build theories of this sort, and supposing you're trying to build it with a minimum of assumptions, you just sort of general kinds of things that are allowed and say this form of equation must describe systems. The one symmetry you're not allowed to assume is time reversal. Okay. Ankur very kindly referred to me as founding this field. What I can say is that me and a few other people to point out that you can have systems out of thermal equilibrium in many different ways. One is you've got a box of stuff, energy in from the outside of the box. Then the stuff at the periphery gets energy directly, and the stuff in the interior gets energy indirectly via the intervening particles. But you instead, or you could, for example, you have a wire, and you connect the two ends to the terminal, and you run a current through it. That, of course, is an out of equilibrium state, but it's one in which the actual driving is imposed only on the edges. The dynamics in the interior is ordinary time reversal invariant dynamics subject to end conditions. But supposing you have a system, for example, a piece of living, which every constituent is directly in contact with a free energy source. So every component particle in the system is in contact with a free energy source. Then that, because everybody is being energized directly, time reversal is broken the individual constituents directly. Each effective particle carries an arrow of time. That kind of system, several of us felt, deserved to be studied separately. Yeah. We call those particles active particles and those systems active systems. So living and their energy dissipating components and some rather amusing artificial are what we call active matter. And for many of us, really the interest was just to say, okay, this is a way of taking living stuff and dragging it into the condensed matter tent. Okay. And what we want to know is how does this class of systems in interesting ways from non-living or non-active stuff. There's lots of reviews on it. These are a couple of recent reviews. There's even reviews and so forth. So back then, when we started playing, I mean, about 8 years into my entry into this game, I rather vainly declared that, kind of a call to arms, like, look, folks, we should work on this class of systems. Naturally, exist. So the interest is in, what are the laws governing distributions? What kinds of phases can you have? If you have two different structures which seem to be in coexistence, just like vapor and what are the laws governing coexistence? What is equal-existent phases? And if you disturb it, how does it relax? What kind of phase transitions are there? And what we and many of my colleagues chose to do was not to approach this from a microscopic point of view where you write down equations of motion for one particle, but saying, look, we know how to study broken symmetry, large-scale physical behavior, mechanical behavior in systems at thermal equilibrium. Let's take the same approach, but remember not to retain time reversal invariance. So you relax that assumption, and then with your write down theories that satisfy all your other symmetries, and see what happens. So that's how we went about it. Okay, so I'll just sort of introduce some fundamentals of active matter. One is both at the level of the individual and at the level of the macroscopic ordered phases, you can have things with different kinds of spatial symmetry. You can have particles, you can have collections of particles essentially described only by the density field of the particles. So these are systems recently constructed in a very, very funny experiment. We just have a surface of these particles. These particles have some internal motor which makes them vibrate. They sort of move really. The interesting thing is if you measure their velocity distribution function, this is a plot of their the probability distribution of their two-dimensional velocity vector. It's peaked at 0 and it has a width. If you just looked at this, you wouldn't be able to if this is a collection of molecules with a temperature like the gas in this room, something that is self-propelled. Because normally when something is self-propelled, you think its velocity distribution will look like it will be peaked on a circle or a sphere of non-zero radius in velocities. Turns out you can have active particles of this sort as well as this sort. This guy's active is certain peculiar persistence of motion, but without a characteristic speed. Sorry, I'm spending too long on the introduction, but maybe it doesn't matter. I don't have to get through everything I'm talking about. Okay? So this is described by, this is a sort of, you can call this scalar active matter. These are vector active matter in a viscous fluid. These fish schools are vector active matter. Also in a viscous fluid scales where viscosity is not too important and inertia is very important. This is an artificial example of active matter. I'll show you one or two movies. And this is an active system in which the particles aren't self-propelled in the sense of moving in one direction. They move forth, but they do so more along their length than perpendicular to their length. It's an object like this, and it has more kinetic energy for moving this way randomly than for moving this way randomly. Which, as you all know from your kinetic theory, is a weird thing that doesn't happen at thermally. Just to show you one or two movies. So this is a surface on which particles have been placed. The surface is vibrating up and down very rapidly. And as you can see, the little tapered, little arrowhead-like particles have all chosen to move in the same direction. If you do the experiment, they sometimes move the other way, sometimes move this way. And there's a medium in between about which I'll say more. This is real living, real live active stuff. It's a fish called karimeen. And you can see this weird phenomena going on here, which would never happen with the molecules of air in this room. And this is those particles I told you about, which have more kinetic energy for longitudinal than for transverse motion. So it's like the longitudinal and transverse degrees of freedom have two different temperatures. And the people whose work is involved are mentioned here. And the other important thing to note, You can imagine studying these systems either moving around on some dry solid surface, bulk fluid, and clearly their interaction is very different because in one case, if one of them speeds up or slows down, it's true that conservation of momentum is involved, but that conservation is a deal between and the whole Earth. And so you don't really worry about it. But here, if you change velocity in magnitude or direction, you communicate that to the ambient fluid, which affects other particles. So we call this wet and dry active matter. Okay. Are there chemists in the audience? None at all. All right. So, a lot of the nice realizations of active matter are chemical. After all, life converts chemical energy to other kinds of energy, including mechanical. And Whitesides and then Aishwan Sen and group made these particles which have on them and put them in a medium with a compound the catalyst. And the result of that is that as long as you keep the compound supplied, you create of reactant across the surface of the particle. You generate flow along the surface of the particle, and these particles start swimming. So that's one fun kind of which we don't work on, but there are people in this institute who do. For those of you who come from a quantum condensed matter background, it's worth noting, let us say, some kind of 2D quantum system, which is this gray square here, and connect its two faces to leads at two different chemical potential, then you're forcing energy through the face of this object. And this little two-dimensional world here is a two-dimensional world through which energy is fluxing. And so the dynamics of this two-dimensional world time reversal breaks time reversal dissipatively. And so it's a kind of active system. And this analogy has been exploited to some degree in, but I will not talk about it during my talk. I just tell you something for everyone in this subject. The approach taken, as I said, is what physicists confusingly call hydrodynamic. What we mean by that term is that we keep track only of those degrees which we call slow in a very precise sense. Characteristic time scale goes to infinity as the length scale of the excitation goes to infinity. The densities of conserved quantities are an example, because if you have something whose integral space is conserved, then at infinite wavelength, it can't change because that's the total amount of stuff there is. Aisha, by the way, you stop me and ask me questions anytime you like. Do you have any questions already? All right. So densities of conserved quantities. The other is what are called broken symmetry modes. In a picture of that, sadly, yeah. So supposing you have a collection of spins in a magnet which can point in any direction and to point in one direction, then if you change that direction globally, the system doesn't know or care. Therefore, if you introduce a perturbation, it looks like you change that direction uniformly, the resulting force or torque will be very small, and so the relaxation will be very small. So conserved and broken symmetry modes are the generic examples of slow variables. Also, if you're near a continuous phase transition, the magnitude of the order parameter also becomes slow. So these are the variables we need to keep track of. So if we have a system with many degrees of freedom, we can take advantage of this notion to approach the theoretical modeling of the system, not by on every detail, but by packaging all freedom into a small number of fields. It's still a problem with many degrees of freedom, but it's packaged very. So I don't know, to the students, is making sense? Speak up if it's not. Do you have any questions? Any worries? Okay, you're not going to answer. I'll have to ask you a question, which I will. All right. So now, yeah. Yeah, absolutely non-equilibrium system. That's the whole idea, right? They are systems with a constant throughput of energy. You keep supplying free energy, they keep doing an energy conversion act and throwing out waste. It's like us.
quantity if you keep on
Yeah, so I mean, within this class of problems, the cases that are easiest, that maybe are the first thing to study, the stationary states of these systems under conditions of power throughput. Exactly. Which is sort of like us in early middle age or something for a while. When we don't, anyway.
Yeah, but the approach that you described
Yes.
is quite generic, need not be necessarily for a
Yeah. So I'm saying that the sort of the things to work on are the stationary states. The formalism is capable of describing whatever you like. You could system where, in practice, after all, we all know that nobody is immortal, and therefore, and any active system needs to be supplied with that free energy. So you can imagine, let's say you have a amount of resources, then transiently the system will behave like an active system, and it will reach an absorbing state known for living organisms as death. Right from back. Yeah, it's ask, what's the natural way to write down equations of motion for these systems? To think about it is the following. Let me summarize all the degrees of freedom into one thing which I'm calling Q, and let me summarize all that's going on in the system. Imagine a system that's chemically driven. Chemically driven meaning the way, like us, it eats food and does something with it. You give it chemical energy. Stepping up this way means consuming one more molecule, consuming one more molecule, consuming one more molecule. So driving a systematically in one direction. And these systems have an internal chemo-mechanical coupling represented by these oblique lines, which means that the mobility in this abstract space isn't purely diagonal. That is, I can push that way, and the chemo-mechanical coupling will make moves this way as well. Pictorially, it's like taking a sheet of corrugated cardboard, tilting it at an angle and putting some object in it. It'll roll in the grooves, which means it'll roll this way. You can use this principle very precisely to take a general collection of degrees of freedom. If you can identify one of them as chemical, or even if you can't, if it's just some additional degree of freedom, you can imagine writing down the equations of motion for a system at thermal equilibrium in this picture, and then saying, no, I won't do that. 1 degree of freedom, and rather than holding the average force on that degree of freedom, which is thermal equilibrium, I hold it at a non-zero value. And if you have this off-diagonal coupling between these degrees of freedom and those, you will introduce new terms in the equations of motion for these guys. And that, without going into any detail, I don't think I have any detail here, is how we, a theoretician with very little knowledge of microscopic physics systems, can write down equations of motion. Okay, we take such and such. I have a flock. It's like only it's out of equilibrium. How do I write down its equations? That's how. It liberates you from some constraints that were imposed on you for writing down dynamics at thermal equilibrium, and you're able to write down terms that were not allowed in the thermal equilibrium case and are allowed now as long as they respect the spatial symmetries. Okay, that's very general, very qualitative. Let's move to our current research, and in the course of that current research, you'll see down equations of motion. So one of the things we've had a lot of is a system in which the act is not the uptake of chemical energy, but a very crude uptake of mechanical energy. These are very macroscopic particles. They are almost half a centimeter long. There's long particles and round particles. For example, put anything you like. The experimental geometry is this this industrial shaker, and you may have heard some of this talks by me before, or you've heard talks by Ajay Sood or one of the others. This part was Roshan's PhD work. It began much earlier in various other students' side. And so this is the experimental geometry. You got particles placed in here, many of them, and you shake this thing up and down at a couple of 100 hertz and like 0.04 millimeter amplitude or something like that. And these particles, because they have trivial shape and because there's a little bit of room above and below, they walk. You keep shaking like this, and the particle starts walking. Okay. So in this particular, in the presence of both the motile particle and the non-motile beads, as you can see, it's plowing its way through this medium. Okay, so it's a simple and kind of somewhat childishly simple energy conversion device. The reason it's not what we're talking about is, as far as the two-dimensional world in which this particle is concerned, it's getting energy pumped through it in a third direction. So its two-dimensional dynamics is legitimately describable as a kind of active matter dynamics. So we can write down the equations of motion for these systems. So I'll show you a rather cool class of phenomena that happened in this system. We took a collection of, I don't know if you can see it, these kinds of particles and these kinds of particles in various experimental geometries. I'm showing you this for simplicity. And we've been working on this system for a long time. Earlier, Nitin, who is not part of this work, Nitin Kumar, Bombay, had shown that if you have a small particles and a fairly large number of these guys can organize themselves into a flock. So you have just 5%, 3% of motile particles. Their movement gets transmitted to each other through the intervening medium of non-motile particles, and you have a phase transition from random motion to ordered motion. We decided to look at a different term here. We decided to look at how these particles affect the density of these particles. So I have to show you a movie, otherwise I'll show you the end result first. What we showed is that if you the concentration of this ambient fixed and fairly high, and you change the concentration of the motile particles from 1% to 2% to 4%, you go from where they're moving at random, and I'll show you a movie, to where this tiny collection of particles all find, they form this little polarized array, and that polarized array can push as many of these as you like. And this is a kind of weird phase separation. This is high density, this is kind of low density. If you have slightly more of the motile particles, they can capture and sequester the region of these particles and create, in effect, low density coexistence. You can repeat this experiment and you will find that the density contrast between these two is usable. It's not an accident of initial conditions. For this set of, you actually get something like, not exactly condensation, at least as far as these experiments go, always ends up being a crystalline, but something like sublimation. And note that these guys, without this tiny, almost homeopathic concentration of these particles, these guys would do nothing. Everything would just move around at random. Without these little particles would not be able to find each other and self-assemble. Cooperatively, they achieve a kind of miracle of this. So let me just show you the movie. I think at the rate I'm talking, I'll get through one topic. Maybe it doesn't matter.
One question.
Yeah.
So is the size of the dense and the non-dense?
Yeah.
It seems that they're not equal.
So that the point is that depends on the total packing fraction, total density. So rather like in vapor liquid, the question you really should ask is the dense and the non-dense, those two regions, how does it work out? In this system, the dense region is to always go to maximum packing. Okay. And then the size is the lever rule, like in ordinary phase separation. And it's kind of fun to watch. So here, nothing happens. Here, these guys have already assembled. Maybe I should show it again. So as you can see, they sort of find each other and condense. And here again, the same thing. So this is a kind of condensation. And so the point is that it's extra strange because, you know, we are all accustomed. Yeah. Yeah. So, I mean, that is, I'll show you. I don't know if okay, on another slide. You could do this at lower densities of beads. You can imagine the concentration of the motile particles at some small value, 2 or 3%, and just changing the bead density. And that functions like an interaction parameter or the inverse of a temperature something. You turn that up and the phase transition takes place. So there are other scenarios where in between you get a flocking state first, but anyway, you know, it'll take me too long. But yeah, the only control parameters that matter here are the area fractions of these two species. The shape speed doesn't matter. It's just like sets a clock speed. It just tells you they're walking fast or slow because there's nothing to compare these. You know, there isn't some other energy scale or time scale to compare them with.
And what about the
Yeah.
what about the confinement?
Vertical confinement is important in the sense that if you don't have vertical confinement, thing will happen.
No, I'm talking about the radial confinement. So because
Yeah,
initially
you can do this in 2 dimensions. The experimental setup in experiments in 2 dimensions is somewhat uninspiring. There are it's you can see in the paper. You can do it in 2 dimensions. You can do a numerical recreation of this with all the mechanics in place and show that even with periodic boundary conditions where the effects of edges are not important, same phenomenon takes place. A large, there is a fully 2-dimensional system will have, you know, a few tens of these little particles, and they all just form one strand. Form a bulk region. They actually form a strand. So it's weird because you have an interface between low density. These guys who are the agents of this phase separation create that interface and sit at it. The phase separation itself or the condensation itself happens only because of these guys at the interface, but the interface happens only because of the condensation. So these particles are not themselves attracting each other. It's a very weird phenomenon. And let's see if we can understand. I don't remember what other slides I have. Yeah. Now to give you an idea, it's also to give you a sort of rather general way in which we. Okay, look, what really matters here? You've got 2 species whose numbers are conserved, so 2 densities. Okay, one of the species has an intrinsic speed. These 2 guys are conserved, but let's actually take a very simple approach. Let's look at only the beads. There's a equation for the beads, and what matters is this current in that continuity equation. Weren't for the active guys pushing them, the beads just sort of jitter around and diffuse. One piece of this current, which I missed a subscript here, one piece is just diffusion. The other piece of this current is that, as you saw, when these polar rods move, they drag the beads with them. And the better their local alignment, the more effectively they drag the beads. So the current is polarization of these beads, of these rods. P being kind of the local. If you take a bunch of these unit vectors associated with these guys, add them up and divide by the number, that gives you some vector, measures the local degree. So you have a current proportional to the polarization. That current, you're moving beads, proportional to the number density of beads, and is proportional to some coupling of to each other. So all that really is now, how do you deal with the polarization? Well, I don't know if I have, yeah. We conjecture and we check that it holds, that because of their shape, these guys, imagine you create an arbitrary density gradient and you start throwing down these rods at random in that density gradient. They will be best accommodated with their pointy end in a high and the blunt end, fat end in a low density. Just out of steric hindrance, right? It will be hard to fit the fat end in a dense region. So if that's the case, you can say phenomenologically, this must be true. The polarization locally must point uphill in density. That coefficient should be positive. If you just take these ingredients together, you've got one piece of the current which says, please beads move in the direction of move from high to low density. This bit that says, beads please move the way P is pointing, and P points the density gradient. So if you crank up this coupling, density or whatever, you should eventually create in which the effective diffusivity, the difference between that guy and whatever comes out of this, changes sign. So the uniform, so you don't know if I have a slide that states it exactly like that. Yeah, so I have it for a one-dimensional case. d rho over dt is div minus div j. J has two pieces. If this piece gets this piece, the relation between j and grad rho will be one that's point in the direction of increasing rho. So what that means then is if you have a uniform state, you perturb it slightly by increasing the density here and decreasing it there, the particle current will be to the regions of increasing density. In other words, it will drive condensation. The uniform state is destabilized with respect to perturbations that make it non-uniform. So that's, and you can work through it in greater detail. So you can do a lot more with this, but if you're doing that, I won't tell you about other problems. So let me tell you, why was this a cool problem? There are 2 or 3 reasons, one of which I forgot to mention because it's in one of my zillions of hidden slides. One, it's a mechanism for something resembling phase separation, which takes place not because of anybody attracting anybody, because of somebody driving. Secondly, it happens only when one of the species is motile. The little pointy particles point in a certain move in that direction. So as they move, they create an in front of them, and they find they are happy with that. So this positive feedback, that's one thing. Second is, it's a general idea that this suggests a general mechanism for creating strong contrasts in density or composition. Does it occur anywhere in nature? This is a silly little experiment. Just after I gave this talk at a conference, I don't know, year or two ago, I can't remember, somebody says, we are doing what are called motility assays. That is, you take the little machines that allow us to move, which are called moleculars, that drive all, movement inside cells and so forth. And there are called microtubules on which some of those motors move. They did an experiment with 2 cells which move in opposite directions on filaments. And what they found was a phase whose pattern looks an awful lot like this. They had microtubules, a single, and they didn't have high density and low density. They had motor species A and motor species B. So the order parameter there was the relative composition, relative amount of A versus B. Essentially, this mechanism comes up in real living matter. We didn't look for it. Our approach was, let's study the world of possibilities given some minimal assumptions, and then do they occur somewhere? Well, turns okay. All right. Let me go to another key. So now I've finished that little. Oh, I wanted to say one more thing. Sorry, I did want to say one more little thing. This mechanism, the rod points to and therefore moves towards the bead. That's one part of the story. The rod pushes the beads. So the rod moves towards the bead moves away from the rod. This can happen in an interaction based on a potential energy, a pair potential energy of interaction. This is fundamentally non-reciprocal, but it also demystifies the notion. There's a great deal of talk currently about the implications of non-reciprocal interactions, and all that work is very interesting. But it's important to realize that non-reciprocity is the rule rather than the exception. Any time it has a chance to arise, it arises. And this is one very, very simple example. All right.
Here, can we assume that because of special type of shape, like one side is pointed other?
Yeah.
So some sort of chirality is
so this is polarity rather than chirality, because this is not inequivalence under mirror. This is inequivalence under just that vector going to minus itself. So I would call this polarity. It's dimensional motion. It means left-right asymmetry, which is then chiral. So yeah, true. Yeah.
And for example, if we consider an ellipsoidal type
of
both the sides,
this whole thing won't happen.
So that will not happen.
Yeah.
So in that case, that symmetry.
So absolutely crucial. Yeah. Because only if something has a polarity, that on general argued ought to move. There's this no Curie principle that you get only those currents which the asymmetry of the object permits. It's not really how Curie says. So let me stick to the theme of non-reciprocal interactions. So with Pankaj Popli and Ananya Moyo, recently we studied the following problem. Many models of magnetism in which you have little and they try to align with each other. Let us say the ith guy and the align by a reorienting torque, let us governed by a coupling Jij, which tries to equalize the angle at which the ith guy and the jth guy are pointing. You can imagine doing that dynamically by an equation of motion like this, right? That if adjacent angles of the different, they will reorient and the coupling will be Jij. If this coupling, if this interaction came from an energy function, product of ith spin and jth spin with some coefficient, then by construction, because it's an energy function, this Jij would have to be. But if I just close my eyes and don't worry about the origin in an energy function, equations of motion, then Jij can be whatever I like. In particular, supposing these guys are actually calling out to each other, signaling to each other, and supposing how well this one can hear that one depends on whether its ears are pointed towards that one and this one. And how well that one can hear this one likewise depends on its ears are pointing. Then any of these signaling based interactions what will happen is it will depend on how this guy is, the effect of this guy depends on how this guy is pointing relative to the line joining these two, these guys, right? And so the simplest model of that is to say that Jij is some constant plus a term proportional to the angle between this guy and the vector joining it to its neighbors. Okay? And now, of course, for the way I affects J, Ji will be some J, Pj dot R Ji. And those two are not the same. Non-reciprocal interactions emerge naturally from any signaling-based coupling, therefore worth considering in all kinds of situations. One of a very famous example apparently is the reason why huge marching locusts line up is because locust here is and that one is trying to run away from this one. So that deeply non-reciprocal interaction is what actually gives you alignment. So anyway, we studied this class of models. One outcomes of that is if you take the continuum limit of the equations of this sort, if you put this P to a field in a continuous space, the dynamics of that P has a term that tries to make the neighboring and has this term. Now, what is this term? Those of you who've seen the equations have seen a term V dot grad V. What does that V dot grad V term say? It says you have a velocity V and you have an inhomogeneity grad V. That inhomogeneity is carried, it's advected by the velocity. So P is able to advect itself pure by virtue of non-reciprocity. None of these guys is moving anywhere in space. So you have transport of orientational information without transport, directed transport, exactly like a velocity field carried without a velocity field. So this is something whose consequences we've been studying. The more formal and nerdy about long-range order I will not tell you about. But in this of systems, if you looked at planar spin models in general, now forget about non-reciprocity, active systems. If you just had a two-spin magnet, then it turns out that at high temperatures, the spin, at low temperatures, they point order, and there's a phase transition from a high temperature paramagnetic phase, low temperature continuously critical phase. Okay? And that phase transition is governed by the binding or unbinding of vortices. Vortices in planar spin models have an interaction energy proportional to the log of separation, and you can put them in a number of places that in the system size, therefore the entropy of that is again the log of scale. The competition between those two logs gives you a binding, which is the famous Kosterlitz-Thouless phase transition. Our question was, what does this non-reciprocity do to that transition? So what we did was to put, or what Pankaj did, was to put in a numerical study of this model, to put in a plus and a minus x. Notice this is something around which, as you walk, the orientation goes 2 pi. This is something around which, as you walk, the orientation changes by minus 2 pi. So this is an oppositely signed pair. At high temperatures, these guys want to unbind. At low temperatures, their attraction wins at thermal equilibrium, and they annihilate, get an ordered phase. Working at temperatures low enough that this annihilation should happen, we just introduced that non-reciprocal bit to the dynamics and showed rather dramatic happens, that for initial processes sitting in such a way that they would normally have annihilated, you find is you put these guys in there, these guys resolutely ignore each other. Meanwhile, because they're ignoring each other, there's time for other vortex pairs to nucleate and eventually proliferate and destroy the ordered phase for even a tiny amount of that non-reciprocal interaction. Since this phenomenon is rather entertaining, I'll just show you the move and move to the next topic. Basically, what happens is, if you put these guys, what happens is that that advection piece creates a wall of distortions, but these guys basically are blind to each other's presence. And if you wait a little longer, what happens is other vortex pairs start nucleating, and then those guys annihilate these. So you had two that were initially separated by a small amount, others nucleated. Some of those guys nucleated these guys, so now you have two widely separated, oppositely signed vortices. So the system basically collapses into a chaotic state, which I will show you here. It's still ordered. The color is telling you direction, and as you wait and watch, you'll find that vortices arise and proliferate. So this non-reciprocity gives you a new path to the destruction of order. It suggests that, as was already suggested in a stochastic PDE study of the continuum version of these models, it suggests a new mechanism for destroying in magnetic systems. Ask, if you look at these non-reciprocal term and the ordinary stiffness, the ratio of those two is clear on dimensional grounds because P is dimensionless. So you might expect that at long scales this wins, at small scales this wins. And indeed, if you plot get a kind of effective, not phase dynamical diagram in the plane of initial of a given pair of vortices and strength of non-reciprocity, you find, roughly speaking, there is a 1/r line which separates the regime in which an initially imposed pair of vortices will annihilate to where it won't annihilate. You can read about that in this paper. Okay. Many reasons, including that Tapan is in the audience, I want to talk about chiral active matter. Part of Tapan's PhD was on active cholesterics. The cholesteric liquid crystal, I'll show you a picture later, is a system in which the axis is spatially periodic. It points this way, this way, this way. As you go a direction called the pitch direction, the optical axis turns statically, and structure of which way the optical axis is pointing. It happens when you take particles that want to align, elongated particles that want to align, but which are chiral. So supposing you took the threaded head of a bolt, threaded shaft of a bolt, and you put a whole bunch of them into a box and shook them. At high concentrations, they'd form a cholesteric. So with SJ, a student, Ananyo and Gareth Alexander, we've been studying these systems. It really started Tapan's work, which was jointly done with Gareth. We then looked at the layered systems that I just talked about, two-dimensionally ordered systems and then three-dimensionally ordered systems. So I'll tell you a little bit about. First of all, for those of you in the audience who haven't read Kelvin, something is if it can't be superposed onto its mirror image by continuous movements, right? That's 3D chiral objects. Because we live in 3D, we realize that 2D chirality can be got around by going to the other side of it. But similarly, if somebody lived in 4D, they could say that about us. Okay, right. And chirality, chirality all over the place in the living world, as all of you know. Another concept that's important here is odd mechanics. Supposing I have a collection of degrees of freedom, positions. Maybe these are components of position in 3 dimensions, let's say, or 2 dimensions. And let's write down a dynamics where I forget about mx double dot altogether. Let's write down Aristotelian dynamics where damping balances the reversible forces. So imagine there's some set of matrix of spring constants, matrix of damping constants, and thermal noise, and write down this. Then you know two things. One is you know that if this came from an energy function, a quadratic form in the x's, then Kij is symmetric. Kij, xi, xj, Kij has to be symmetric. You know that if this damping for a system at thermal equilibrium, then the covariance of the noises and the damping matrix have to be strictly proportional. This is symmetric, so this is symmetric. Or you can say it in many other ways. With this dynamic, with these rules, the purely inertia-less dynamics of particle positions in potential or any potentially cannot be oscillatory. It will always be. However, if you break either of these strongly, you can get oscillations without inertia. That is, you can have the x and the y coordinates of something behave with each other, the position and the momentum of something. See, x and y are they're both time reversal invariant, right? So they can't beat against each other and produce oscillations normally. But I'll show you that in active systems they can. You already know of another example where something similar happens not with positions but with velocities. If you write down the dynamics of a charged particle in a magnetic field, you know the x and the y components of the velocity. If you have a magnetic field Z, beat against each other, and that's how you get cyclotron orbits. Okay, and there also it's happening because you broke time reversal invariance. You broke time reversal invariance by the magnetic field. Okay, so here we're going to break time reversal invariance not by a magnetic field, dissipatively. Okay, this odd mechanics again is enjoying a great deal of attention these days. Goes back to quite old work by Gustav Rohn about 25, 30 years ago. And there's also a lot of studies of this kind of thing. There was an earlier period when people studied systems homogeneously driven out of equilibrium an awful lot. A lot of us were interested in pattern formation. The canonical system for studying pattern formation was a layer of fluid heated from below. You've seen the cellular patterns on the sun, or you looked at on hydrodynamic and hydromagnetic stability. Those patterns, think of that system as a quasi 2D system pumped through it in the third direction. Saucepan on the stove, energy pumped in third direction. Patterns on that surface are a kind of active matter pattern, you can call it that. You can rebrand it that. So people had already looked at odd mechanics without calling it that in that context by looking at rotating convection. So if you have convection together with some pattern breaking, you can get all kinds of cool odd effects. Nonetheless, this subject is hugely exciting, partly because of some very beautiful experiments on star oocyte aggregates and so forth. And so I'll tell you a little bit about it. Very oddness is clear to you. And odd damping is something that all of you have seen, the swing of a cricket ball. So I can just tell you the kind of thing we do. Basically, we're interested in phases with 1, 2, and 3-dimensional translational order with chirality. The chirality here is the twist of the optical axis. Chirality here is not so clear, but if you take a columnar phase made of which are intrinsically chiral and all the same chirality, for example, a bundle of axons, microtubule bundles in an axon, or in which this kind of twist, when you have double twist cylinders in 3 directions, twist cylinders in 3 directions, you can get 3-dimensional phases, which are 3-dimensional crystals made up of complicated defect structures that arise when you try to make this twist in multiple directions. These are called the blue phases of. Our interest was in asking what happens in any of these systems. What is the hydrodynamics of these systems? Hydrodynamics get interestingly modified when you introduce active forces. So I will not labor that very much. One of the fun, turns out nobody had really worked out a complete hydrodynamic theory of these phases, even though I remember experimentalists asking me to collaborate on such a project when I was a postdoc, which was more than 40 years ago. And I do so because I fell ill. And maybe because the problem is so horrible, nobody has actually done it properly since then. So we made a stab at it. If you have a system that's like this, just one-dimensional periodic, you know that, and you know this for the sharp. If you turn it about this axis, effect is the same as translating along that axis. That's what we mean by a screw axis, right? If you take a bolt and look at the thread pattern, if you turn it, it looks like you moved it up, right? So there is this thing, screw axis. So we argue that systems of this sort behave as though they have 3 screw axes, and we therefore down the effective hydrodynamics of a system like this. That's the displacement field of the periodic structure. That's the velocity field. That's the equation satisfied by the velocity field when you ignore inertia. The rotation translation coupling in the displacement equation, an interesting curl force in the momentum equation, and the end result is a class of instabilities which arise if you introduce activity into these systems. Characteristic growth rate whose dependence on wave number, that is 2 pi over the wavelength, we can predict. And there's various other kinds of fun. It's too technical to go into any of this, but there's this bunch of papers that you can read about them. So I think what I'll do is I'll skip to the end, I'll skip all this because I'm out of time. So summary, I told you, I've been telling you basically about dense matter, and I've shown you that you can actually do predictive theory on these systems very much about the microscopic details. And that the fact out of thermal equilibrium generates phenomena that are at least maybe deep and maybe of practical relevance. And I told you about non-reciprocal interactions, new kinds of condensation. I told you about motile chiral particles, and I did not tell you about this last bit, which you can read about. So I'll spend the last negative amount of time about sort of the frontiers. So there's different kinds of directions. Look, this is a class of non-equilibrium physics problems. What types of problems in that domain remain to be solved? So one big class that people have not done very much about is applying these kinds of ideas to fluids on large scales where inertia rather than viscosity dominates. Turned out that there's some instability we predicted about 25 years ago on small scales where viscosity dominates kind of took over because people saw that kind of phenomenon in simulations, then they saw it in model experimental systems, and they just went to town with it. But you can ask, instead of looking at bacterial or subcellular phenomena, supposing you look on very big scales, like a school of fish, which was our initial motivation. Happens in active systems where inertia matters. We've done some work which I think is quite interesting, but there's really not been a clean experimental system on which you can turn a knob and change some important control parameter and see what happens. Can we control flows in these active systems by introducing structure, by shining light somewhere, those kinds of things? Can we use functionality into these systems in the form of information processing? It turns out you can various kinds of smart active matter. There's talk than action. People do this kind of thing in very simple systems. I cannot claim, even though I really like this field, I cannot claim that any of us, not just us, but even other groups, has really made a breakthrough where they can say, okay, here is an autonomous active system that executes tasks. Okay. Similarly, introducing evolution is something that's worth doing. A more general outlook, yeah, I guess I should have had these in the opposite order. So coming back purely to the physics end of active matter is, again, this notion of can we write down tractors in which we introduce signaling and sensing in some very simple way, discover outcomes that somehow enlighten us in some way. A very fundamental physics question is this. Let me retreat again to a simple example of the fluid heated from below problem. Suppose you have a layer of fluid heated from below and maintain a temperature difference in bottom and top, then you all know that if that temperature difference is small, you just get conduction. And if the temperature difference is big, you get convection. That's an example of small-scale breaking of time reversal invariance, namely the mere existence of a heat current, is always there, but it's only when it crosses a threshold that it gives rise to macroscopic manifestation of broken time reversal, namely convection rolls. So, can we say something in this class of non-equilibrium statistical mechanics about when small-scale broken time reversal affects large scales? We have sort of tacitly assumed that when we take one of these active systems, like the liquid crystalline systems that I showed you, that we know how to choose the slow variables. I gave you a prescription. Conserved densities of conserved quantities, broken symmetry variables, and amplitudes near a critical point. That's fine for dead matter, but living matter, the sort of the parameter values in things like tissue or living systems have been chosen as a result, have emerged as a result of evolution. So, and therefore they're non-generic. So do we have any different principle that will guide us to the choice beyond the ones that work in equilibrium systems? And answer is, people have said that some class of systems evolve values to a critical point and so forth. I don't know. Okay. Relation to other kinds of matter like open-driven quantum systems, etc., is something that's worth exploring. Lots of purely technical challenges, by which I mean the following. Problems in which you sort of know roughly what happens, but you cannot calculate the scaling functions, exponents, behavior in a phase, behavior. You know the mathematical problem, you know the field theory that's supposed to describe it, but none of your solution methods is any good at giving you answers. So there's many of those. There's even violent disagreement, and the disagreement is violent. One side is right and the other side is wrong. And anyway, on the scaling property, simplest model of flocks. And okay, with that, I'll stop. Thanks.
There will be an active question answer session, I know, because many of the students, I'm hoping, are teeming with questions. But before that, I will the chair to present this small token.
That was great.
Thank you. Thanks a lot. Thank you. Thanks.
Keep it for you.
Oh,
I
sure.
think it's time for some Q&A.
Sure.
Okay. Students, up. You can start with what is called active matter, even though we have described it.
Yeah.
So in the initial slides, you showed 4 videos. Among those, I think the first one or the second one, the particles move along the periphery. Why do they move along the periphery?
Okay. That's a question. Actually, maybe I'll just show it again. It's a use this. What is it? Yeah. Really, what's happening here is that something that's self-propelled and sort of moving directionally, if it's in a bounded domain, it'll always reach the edge, right? And even if noise kicks away from that edge, it'll end up reaching another edge. And if noise kicks away, it'll. So the problem is in any of these confined geometries, there's a certain amount near the edge is inescapable. With this geometry, some amount of re-injection into the bulk is very nicely taking place, so it's the edge. So it's just, and that's why we were suspicious. So Harsh Soni recreated this class of systems in a computer, not by sort of putting the equations in, but by putting in Newton's laws for particles with shape, with inelasticity, and with static friction, and with a base, with a lid, and with sidewalls. It's a sort of I don't know why he ever forgave me for asking. It is a heroic reconstruction of the experiment, but with periodic boundary conditions instead of edges. And the phenomenon then takes place homogeneously in the bulk. So the phenomenon is not because of the edge, but this edge physics is interesting actually. Another part of the talk I didn't tell you about is these little chiral active particles in the same class of systems. If you take those, bend them a little bit, then they start going around in circles. And then you get physics of skipping orbits at a boundary, like in charged particle, like in the Bohr-Fan experiment. So you can have a lot of fun there. And you get something like the skipping orbits, but I don't know how many of you know, if you have a charged particle in a magnetic field, Brownian particle, then you know that it wants to do cyclotron orbits in one direction. You might think, therefore, that tells you that you put on a field and you get a diamagnetic moment. Answer is because you have only two choices. One, you have an unbounded system, in which case it's never really. Two, you put on a boundary of any kind of confinement, and then you have orbits one way. Those same orbits at the boundary become the skipping orbits. They exactly cancel. The reason you know they exactly cancel is you can write down the Hamiltonian for a charged particle in a magnetic field and calculate its partition function, and you can eliminate the magnetic field by a change of coordinates. So you know the field couldn't matter. That's what Bohr and Van Leeuwen in her PhD thesis showed. Here what happens is skipping orbits completely take over. So you get, essentially, if you've got these chiral guys, they all hang about at the boundary. So you gave me the excuse to tell you about that. Yeah.
And what is the medium in which they propel?
It's just beads. These are, the beads from some Rakhi manufacturers in Gujarat or something. I think something like that. That may have changed more recently, but yeah. So I mean, this is very, very macroscopic physics. What's fun is, honest to God, phase transition physics takes place even in this system. That's kind of interesting.
Thank you.
Yeah.
Hi, sir. Sir, I have a doubt. All those things you have shown, is it experiment or the only simulation?
I think everything I showed you today was experiment. I don't do the experiments. I collaborate with experimenters who do them. But I mean, I'm seriously involved in the experiments. I don't think I showed you even one simulation. I think all of it was to God experiments. It's a big industrial shaker. Shakes up a couple of 100 hertz. And that's just a way of supplying these particles. So each of these things, you may have seen Supposing you take your on a table and you put it on vibrate, always turn in one direction because it has some net chirality. That net stray allows you to preferentially converts the random input of vibrational energy into directional motion. The direction there is handedness. In the case of vectorial shaped particles, the direction is a vector rather than a left to right. Yeah.
One more question. That changed the density to 1%, 2%, and 4%. You
Yeah.
have shown there.
Right.
There 1% we can see all that are not accumulating. In 2 it is accumulated, and in
Yeah.
4 was a little bit of different thing from second and first.
So in 4, what happens? You get two of these little moving edges, and they capture these. So in there was too few, you got one edge, and it moved all these particles like this. When there's a little bit more of them, and we've tried adding more, you don't get more. You just get more accumulation of the same stuff at these. We don't. There are many things we don't understand about it, but this is what happens in that one.
Is it because of the middle of the some beads you are
Yeah.
that beads are the only reason for the two accumulation, or anything else?
That's all. I mean, whatever you have in the system is that the tapered particles have a tendency to move in the direction in which they're pointing. The beads sort of bounce around and don't do much, but these things come in each other's way. See, just like, I mean, the fact that the beads form a surprising, hard spheres form a crystal when you pack them, right? The surprise is that the motility alone, motility plus extruded volume alone, is enough to create these different phases, if you want to call that.
Thank you, sir.
Sure, thanks.
During the establishment of this field, the initial motivations are to look at non-equilibriums, right? Were you inspired by living matter or?
Yeah, no. So for this little sub-inspiration initially really was to look at flocking phenomena. So I mean, there were 2 or 3 things going on. Actually, there's a bit of history and backstory. One is people have been interested in flocking as a sort of phenomenon, as a phase transition, as a weird kind of crystalline order. That was Toner and 2 around 1995 or so. People were interested in fluctuating membranes as a statistical mechanic. People started introducing active processes in those problems. So supposing, let me give you, so there were 2 or 3 directions really, I would say. Flocking, which is not non-equilibrium system, but coherent motion. 2, molecular motors. People knew in Curie Institute and so forth were very interested in molecular motors, which are the motors, those are the all movement to happen. You know, all muscular movement is because of motor protein. That was another direction of interest. Another was physicists had got interested in flexible fluid films as a statistical mechanical system. And then some people then realized, look, we really should be putting in non-equilibrium processes into this. Any real cell membrane has actin polymerization sites, ion pumps. Those are all actively energy objects with a vectorial asymmetry. They'll drive the membrane in one direction. And if so, what happens? So in the early to mid-90s, people had started doing that. Working on the active membranes problem around 96. We finally published it in 2000, I think. So the motivation wasn't just general non-equilibrium physics. It was very much the living world. Living things, motile organisms, protein motors. Those really motivations. And there's actually another really fun piece of history, which is that more than 50 years ago, 1969, 2 fluid dynamicists, Finlayson and said, you know, we know about instabilities in systems when you drive it by external gradients. What about fluid dynamic instabilities that take place due to internal energy conversion from chemical in living matter? This must be happening. It to write down equations of hydrodynamics for these systems. There are stresses that you can build out of the existing variables. And they said, this is a new field. Everybody should come work on it. paid attention to them. It's a fantastic paper. It tells you what happens sometimes when the time is not right, or when some formalism has not yet been developed. So what I claimed was a manifesto that I announced in 2010. Something very similar was in these guys' paper. They said you'll need a new kind of statistical mechanics and thermodynamics to do this. This will be, complex fluids research should be, should heavily involve itself in this. They said all this stuff, and they even gave examples of the hydrodynamic scalar active matter by building stress tensors. So you want to build a second-rank tensor, and supposing you only have a concentration field, you'll have to take grad C, let C be the concentration field, then grad IC, grad G, list second-rank tensor you can build out of it. So supposing you build a term like a thing and write down the most general out of equations. These guys did that. They predicted instabilities. Basically, nobody came to the party. And one of the reasons was, 1969, the idea of writing down dynamic equations for anything with degrees of freedom other than a velocity field or other than a velocity field and a magnetic field, if you was just not there. The general principles of broken symmetry hydrodynamics that Martin Parodi and Prashant wrote down in 1972 didn't exist yet. They were 3 years before that time. That's all. But that paper sank without a trace. I found it by accident, looking for something on the Curie principle. So I think most of the people who know about that paper know it only because I found it and told them about it. So that same motivation, let's do the hydrodynamics and stat mech of living matter, was very much there 50 plus years ago, but nobody took it up.
Thanks.
Okay, I think so. Let's take two more. Okay.
And nice talk. So I have two very basic questions.
Yeah.
In the chirality, so here, in the chirality, non-reciprocal model that you are showing.
Yeah.
I have my first question is that there will be some sort of phase transition. What is the nature of that, and is like continuous second order like or first order like? And
so yeah, so okay, you have more. Is there more to the question?
That, if so, if they follow, does they follow different driving conditions or driving magnitudes?
Yeah, driving magnitude itself can be an important control parameter. In many of these problems, as in all out of equilibrium phase transition, often we don't even know what it is that has to be minimized, what principle to really use. We can write down partial differential equations with noise, find sort of mean field plus fluctuations kind of treatments. People in some instances have done a more thorough analysis. The most interesting, if there's one single interesting thing that stands out, is that non-reciprocal and often chiral systems are characterized by a type of phase transition called the exception phase transition, which is a place at which two eigenvalues and two eigenvectors, the corresponding eigenvectors coalesce. Interestingly, this type of phase we unearthed a very, very long time ago when we were looking at not a strict active system, but if you have a collection of particles driven uniformly in one direction through a dissipative medium, then maybe I can. So I mean, not to take credit of it. Oh, it's there. Sorry, yeah. Maybe I can just write. Great. So supposing you've got a long, I'm just doing it in one dimension. Supposing all these guys are being driven in some direction, and there's some medium, about its detail, just think it's a medium with enough degrees of freedom such that the way a particle moves, the speed at which a particle force depends on its environment. I mean, you know that if you have two particles settling in a viscous fluid and an isolated particle, that kind of thing. So supposing you have this system, supposing you say, let's perturb slightly about this precisely, a periodic irregular state. Supposing these guys are slightly closer to each other. then they'll fall slightly faster. So at the next instant, these guys will be ahead of their neighbors. And now you can say this region and this region are, I'm drawing it badly, this region and this region, you can composite tilted objects. So you have a tilted object and tilted object being driven on general symmetry grounds. This is a handed system because it's tilted and it has a vector like that. So it knows left from right. Therefore, on general symmetry grounds, either these guys will move a little bit like that, or they'll move a little bit like that. We don't know which a priori without knowing the detailed dynamics, internal dynamics. What we do know is, therefore, this system admits a phenomenological parameter whose sign tells you whether initially closer together or moves farther apart. If they move closer together, you have a clumping instability. If they move farther apart, that means this little perturbation will travel as waves. Waves not because of inertia, but because of this coupling between configuration. If you treat that as a tuning parameter, you will go from the wave state to the clumping state through a point phase transition. This was we didn't know it is called it back then, but my Rangan Lahiri, who is no more sadly, worked on this class of problems. So that transition turns out to be a very, very simple example of an exceptional point phase transition taking place indeed in a non-equilibrium system. So that's maybe the single most conspicuous phase transitions and active or non-reciprocal system phase transitions is this exceptional point physics. That's one interest. Sorry, I shamelessly took the chance to give a plug to Kawaz. No.
Okay, one more student. Yes.
Hello, sir.
Yeah.
So one slide where it was mentioned that this continuum can be extended to wave density. Show that slide.
I have to think now.
Density wave, I think.
Oh, yeah. Okay. Yeah, got it. Okay. So what I was saying is, okay. I didn't tell you in detail. Point B, supposing you want to describe, these various kinds of ordered phases, and you want to build a hydrodynamic theory of these. The way we go about it is to write down equations for we can describe these structures. I shouldn't even say density wave. We can describe these as modulated phases of some structural quantity. It would be the optical axis. In these things, it would be the optical axis or the defect density or something like that. We can use principles similar to how you write down a density wave theory of a crystal, a la Ramakrishnan and Yusuf. For these systems, we have to choose the field correctly. We could say, imagine a system that has a density and a chirality and velocity fields. Write down the dynamic system in a fluid phase, introduce a free energy that makes it want to condense into some kind of translationally ordered phase, develop the dynamics, small disturbances about that ordered phase. You will then get equations of motion or a displacement field of that phase. That's all I was trying to say. That's what I was trying to avoid writing down the equation just by saying that rather than just one or two particle coordinates, you have to have whole fields.
So one more question is that here.
Yeah.
The one slide where we had that ring and filled with beads, and then we had that small structures with arrows. So can the same thing happen? Let's say the particles have some sort of potential distribution, charge particles.
So which I have to figure out which slide you're talking about. What was there? There was
we have a ring structure.
That okay. Yeah. So this, for example, right?
So, for example, let's say all the particles, if we think, let's say, galactic structures, they can have a gravitational density. So can the same thing happen in?
So you can get this kind of compensation for many reasons, but it's hard to think of a case where that small concentration, what appears to be not even an extensive quantity of the condensing agent, is able to produce an extensive effect. Now, I'm not claiming the principles of, I'm not. I can't give you in right a sort of homeopathic concentration of these motile agents can create an infinite condensate. That I don't know. Condensation can happen for many reasons. After all, gravitational collapse is a kind of condensation. Or if you have particles moving freely in space and then colliding inelastically and sticking, condensations. You can get condensation and shock formation for many reasons. What is special here, is that these particles condense only because they're being pushed by, and that you are able to produce this, what seems to be a phase transition, with a quantity of particles whose proportion to the whole system seems to go to zero in the infinite size limit. And that's really weird. I don't know if it's true, but that's what intrigues me about this problem.
Thank you.
Okay, I have seen a lot of hands, but unfortunately we have to. So I'm very sure that he would have loved to take more questions, to ask more questions. But for today, let us thank the speaker and
Thanks a lot. So I should get out of the network and stuff, right? Yeah.